Hello, and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about the source-free series RLC circuit, example number 1, where in the next video I would do another example to really drive home this source-free series RLC circuit topic. And in this example, we're tasked with finding this I of t, considering that the circuit has reached steady state at t is equals to 0 minus. And essentially what's happening here is that my switch has closed and we want to derive what's happening to I of t is equals to 0 or t is equals to 0 minus. And then when this switch opens up, this capacitor has been charged via an electric field, and this inductor has also been charged via a magnetic field. And that's when we get this source-free series RLC circuit when this switch is open. And I'll post a video of our past videos that we studied this in the top right hand side corner of this video. Okay, similar to the examples I've done in the past, I encourage the viewer to pause the video and try and solve the problem and then come back to the video and see if they got the correct answer. Okay, to begin, we need to consider a case number 1, or when t is less than or equals to 0. And essentially this is when the switch is closed. And we can draw our circuit like this. And I will explicitly put a short circuit here for my inductor. So I'll make it purple. This here is 10 volts. This is 4 ohms. This is 6 ohms. And as you can imagine, at steady state, that capacitor is an open circuit. So no current is going to flow through this path. So then that means that all my current is going to flow through this path here, I of t, or simply just I. And now this part is very important, but if you remember, the voltage we're concerned about is from this node here, call this A, and put this as a plus, to this node here, or again here, call this minus, and this is that V of t. And it is the same voltage across this resistor, which is here A and here B, where again, let me call this node here B. So we can say that V of t is also the voltage across this resistor V of t. And I hope this makes sense. Again, that's because voltages are the same in parallel, and I've talked about that in a previous video, which again, I'll post in the top right hand side corner of this video. So then what can we say? We can say that at t is equals to 0 negative, or basically just 0, we can say that I of 0 minus, which is equals to I of 0, or my initial condition across my inductor, this component here, is equals to 10 volts, which is my voltage source, plus my equivalent resistance, so 4 ohms plus 6 ohms. So essentially this is 1 amp. Note that this is the initial current through the inductor. The next thing we want to find is this VC minus, or again, VC of 0. And essentially this is just 6 times I of 0. Again, because it's the voltage across the 6 ohm resistor. So using ohms law as my resistor times my current. And since I of 0 is 1 amp, this becomes 6 ohms times 1 amp, which is simply just 6 volts. And essentially this here is the initial voltage across the capacitor. And again, remember from our past video, we need 2 initial conditions because we have this inductor and this capacitor here. And in order to satisfy our final I of t equation, we needed 2 initial conditions. So this is it for case number 1. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. Okay, so the next case we want to consider is this case number 2, or when t is greater than 0. And essentially, this is when we disconnect that switch And my circuit now becomes the source-free series RLC circuit. Specifically now, because my capacitor is charged up and my inductor is also charged up. Where again, this was 0.02 farad. This is 6 ohms. This is 3 ohms. And this is 0.5 Henry. So what I can do is notice that this 6 ohms and this 3 ohms are in series. So then I can add them up. So then this becomes 9 ohms. And essentially we can get rid of this 3 ohms here and this becomes just a wire. I hope that makes sense. So then to see what category this source-free series RLC circuit falls under, whether it's overdamped, critically damped, or underdamped, again, which we've talked about in the past, we need to consider this alpha, which is equated to R over 2L, which is again, R is 9 ohms over 2 times 0.5, which is then equated to 9. And this is in nepers per second. And if you remember, this is what's called the damping factor, or also referred to as the Napier frequency. The second parameter that we concern ourselves with is this omega naught, which is equated to 1 over the square root of my inductor times my capacitor. So then this is equated to 1 over the square root of 0.5 times 0.02, which if you do the math is 10 radians per second. And this here is referred to as the resonant frequency, or a pretty long name, which is the undamped natural frequency. Given these two values, we can say that alpha is less than omega naught. So then we say that this is my underdamped case, where now we talk about S1 and S2 equating to minus alpha plus or minus the square root of alpha squared minus omega naught squared. So this is minus 9 plus or minus the square root of 81 minus 100, which is equated to minus 9 plus or minus 4.359J, where we talked about this 9 being this alpha, or again, this damping factor, and this 4.359 is omega D, or my damping frequency. So then from previous video, we say that I of t for the underdamped case is equated to e to the minus 9t times a1 cosine 4.359t plus a2 sine 4.359t, and this here is in amps. And let me go ahead and call this equation number 1. So now we need to find these constants A1 and A2 using my initial conditions. So the first thing we could say is that I of 0 is equated to 1 amp, which we saw from the previous slide. And this is equals to e to the minus 9 times 0 times A1 cosine of 0 plus A2 sine of 0. We can also see that e to the negative 9 of 0 is just 1. Cosine of 0 is 1, and sine of 0 is 0. So therefore, 1 is equated to 1 times A1 times 1, or simply A1 is equated to 1. So this here is my A1. Now to solve for A2, it's a bit more tricky. And essentially, we need to find di of 0 over dt. In order to do that, let me take this circuit here and say that I have a current I flowing through it, and there's a plus minus here, there's a plus minus here, but here there's a plus minus. And again, remember that V of t from our previous slide that flowed through my capacitor and my resistor. And let me go ahead and write a KVL in this loop. So I can say that this is minus VC plus VR plus VL is equated to 0. And again, this is minus because my current is going into the negative terminal of my voltage VC of t. So then we can say that the voltage through my capacitor is minus 1 over C integrated from infinity to T I of dt, plus the voltage through my resistor is just Ohm's law, R times I, plus the voltage through my inductor is L di over dt, and this is equated to 0. We know that this voltage here has an initial condition V of 0, right, from our previous slide. So then we can say that minus V of 0, because that's the initial voltage through my capacitor, which we proved in the previous slide again, plus R times I of 0 plus L di of 0 over dt is equated to 0. And essentially, if we just solve for di of dt, we get di of 0 over dt, which is equated to minus 1 over L R I O minus VO. I hope this makes sense. So then this is equals to minus 1 over my inductance is 0.5 times my resistance is 9. IO is 1 minus my initial voltage is 6. And if you do the math, you end up getting minus 6 amperes per second. Again, that's because it's a derivative, right? It's current over time. Something very, very important to note is that in the video that I did labeled the source-free series RLC circuit clearly explained, we considered that the current is going through the positive terminal on all my passive components. As a result, this equation here is actually going to be VC plus VR plus VL is equals to 0. And if you do the math on this, you get that di of 0 over dt is actually going to be minus 1 over L times RIO plus VO, or the initial voltage across the capacitor. And the reason why I wanted to point this out is because this problem we're doing right now is a tricky problem, and that was the trick. So a lot of students might have ended up putting a plus here, which is not correct. You would get the wrong answer. And I hope that me sort of explaining this makes sense. If you have any questions or concerns, again, please leave them down in the comment section below, and I'll be sure to get back to you. Let me go ahead and fix this so there's no ambiguity. And essentially, before we go to the next slide, because I'm running out of room here, note that I prime of 0 is equated to minus 6a over s. And we will need this to find A2. So that's the direction that we're going towards now. Okay, I've gone ahead and rewritten the I of t equation. Again, remember A of t is that 1. And we're trying, or the goal is to find A2. So in order to do that, we need to find the derivative of I of t. So di of t over dt is equated to, we're going to take the derivative of our first term, so minus 9e to the minus 9t times a1 cosine 4.359t plus a2 sine 4.359t. And again, this is just a product rule, plus I'll leave the first term alone, so e to the minus 9t. And when I take the derivative of what's in the parentheses, I'm going to have a common term of 4.359, and this is going to be times minus a1 sine 4.359t plus a2 cosine 4.359t. That's just the product rule again. So I hope that makes sense. So then we say that at t is equals to 0, we know that di of 0 over dt is equated to minus 6. So then this becomes, I'm not going to write it out like I did for the A1 case. I'm just going to talk about it. This becomes minus 9 because e to the minus 9 times 0 is 1 times A1 cosine of 0 is simply 1 plus sine of 0 here is 0. So this is 0 plus, again, a minus 9 of 0 is 1. So 1 times, I leave my 4.359 alone, times minus 0, because this is sine of 0, plus A2. We know that we can plug in A1 is equals to 1. So then we're left with minus 6 is equated to minus 9 times 1, because A1 is equals to 1, plus 4.359 times A2. If you do the math on this, you get that A2 is equated to 0.6882. And finally, therefore, we can say that I of t is equated to e to the minus 9t times 1, but I'm not going to write the 1, cosine of 4.359t plus 0.6882 sine of 4.359t, and this is in amps. So this here is your final solution, and on most homeworks or exams, this is the solution that you would normally give. But let's go ahead and take it a step further and go ahead and plot this on paper and also plot it in decimals so we can visualize and actually see what this function is doing. And the first thing we need to do is notice that our time period t is equals to 2 pi over my damping frequency, omega d. So this is equals to 2 pi over that 4.359. So then this is equals to 1.441 seconds. And then another thing we need to do is notice that my tau, or my time constant, is 1 over alpha, which is equals to 1 over this 9 here. So 1 over 9. So this is equals to 0.111 seconds. So when we go ahead and plot this I of t, it's going to look something like this on paper, where again, this is I of t and this is t. I'm going to plot it in red. I'm going to say that it's 0 and then it shoots up here to 1, because again, remember, there's two things we care about. My initial condition I of 0 is equated to 1. We know that, so that's why it comes to this 1 here. So the next thing we ask ourselves is, when does I of t equate to 0? So when on this timeline are we going to get our first I of t is equated to 0? And we know that this is equals to e to the minus 9t times cosine 4.35t plus 0.688 sine of 4.35t. We can go ahead and cancel out this e to the minus 9 by dividing on both sides. We can go ahead and say that this is then cosine 4.35. I'm going to go ahead and put the 9t since I have room, is equated to minus 0.688 sine 4.359t. If I divide the cosine over on this side, I get that my tan of 4.359t is equated to 1 over minus 0.6882, which is approximately minus 1.453. So we're almost done here. We have 4.359t is equated to the tan inverse of minus 1.453, which if we do the math on this, we get minus 0.968 radians. And this is very important. Since time moves forward, we need the first positive angle where the tangent function hits the same value. Since tangent repeats every pi radians, or 3.14, we add pi to this value here. So essentially, 4.359t is equated to minus 0.968 radians plus 3.14 radians, which is equated to 2.173 radians. And so then t is equated to 2.173 radians over 4.359 radians per second. Again, remember this value here was my damping frequency, and frequency is in radians per second. So then this is 0.4985, or approximately 0.5 seconds. Now you might be wondering, why did we do all this to find T? And again, it's because we want to find out where on this T-axis does I of T go to 0. And now we know exactly where. It's going to be at this 0.4985. And now we know that if this thing is going down here like this, we know that it's going to come up and start to dissipate. But then when it comes back here and makes one period, it's going to be this value plus my T, or my time period. So plus 1.441 seconds. So it's going to be around 1.939. So let me go ahead and raise this. So you might be wondering, where is this point? It's essentially just this point plus T over 2. And T over 2 is 1.441 over 2, which is simply just 0.7207. And when we do the math on that, we get that this is 1.219. So then we can erase all this. So now the last thing we have to ask ourselves before we plot this in Desmos is, where is this minimum and where is this maximum? And essentially a good rule of thumb, which we'll see in the Desmos, is that this minimum here, so from here to here, this is the minimum, is going to be this value plus tau. All right, so it's going to be 0.4985 plus this 0.111 seconds, so plus 0.111 second. And when you do the math on that, it's going to be 0.6095. And essentially the same thing for this maximum here. If we want to calculate this, it's going to be 1.219 plus tau, which is 0.111, which is approximately 1.32. So again, this here is 1.32. I'm not going to show this explicitly, but if you plug in I at T is 0.6095, you're going to get minus 2.3 milliamps. So essentially, we're going to plug 0.6095 into this equation here. And this is what you receive, that minus 2.3 milliamps. And then lastly, if you plug in I of 1.32, or this value here, you're going to get 4 microamps. And again, it's important to note that in this graph, I have proven that I of T in this source-free series RLC circuit starts off at 1, but then it decays as time goes on. From 1, it goes to this minus 2.3 at some point, and then when it swings back up, it's losing energy, and it's at this 4 microamps. And again, it's losing energy to the resistor, which we talked about in that previous video. And essentially, it's going to keep going until it saturates at I of T is equals to 0. Okay, so the last thing we want to do is just grab this in Desmos for completion. Okay, let's go ahead and do this in Desmos. And I like to do this because it kind of shows you a cleaner picture than the handmade one I did in the previous slide. So this is T less than or equals to 0. We want it to be 0. And then for T greater than 0, we want it to be e to the minus 9t times cosine. We said it was 4.359 t plus 0.6882 sine of 4.359 t. And then we close that all up. And let me go ahead and increase this so you can see the whole function. And again, as you can see, it does saturate really quickly, right? But if we zoom in, we could see that it does swing to the negative value. And what specifically we can see is that it hits 0 at that first point, which we calculated, which was that 0.4985, which here they're getting 0.4986, which is fine. Another important parameter, which it hits its minimum, right? And then it starts to swing back up, as you can see here. Maybe I can move it to the right a little bit, right? So we can see it starts to swing, and we get that minus 0.0023, which is essentially minus 2.3 milliamps. So that's accurate. But the only caveat is at the time that we get it is at 0.602, where we got 0.609, which again is a very small difference. So that could be neglected. So this point makes sense. So then let's go on to the next point, and we can see that it's right here. Okay, so let me click here, and we can see that, okay, so this is at 0. The next point is at 1.219, which is what we got, and that's at 0. So that's exactly what we got. And again, it starts to come back down at t equals to 1.32, which is exactly what we got. And again, you can see that it's at positive 4 microamps. So that makes sense. Okay, so I hope this example helps. I hope that me graphing it on the paper and showing you where the plots are and then correlating it to Desmos aided you in visualizing what this underdamped system is actually doing in real time. If you have any concerns or doubts, please leave them down in the comment section below, and I'll be sure to get back to you. If you liked the video, please give it a thumbs up, and please share the video to your colleagues and friends so that they can also obtain the knowledge given in this video. Lastly, if you like what the YouTube channel is providing, please consider subscribing. It really helps the algorithm. Thank you.